So now we'll study the simple pendulum. So simple pendulum is you have a small mass m and you connect a string of length L and suspend it from a rigid support. Okay. So consider a simple pendulum which consists of a particular mass m, which is called bob of the pendulum, and suspended from one end of an unstretchable and massless string of length L that is fixed over here. That is fixed over here. Okay. The bob is free to swing back and forth in the plane of the base over here. In the plane of the base, to the left and right of a vertical line through a pendulum. Pendulums through a like vertical line through a pivot point over here. So it will move back and forth over here. The forces acting on the bob are the force from the string and the gravitational. So there are two forces. One is tension T, another is gravitational force. Okay. And gravitational force will be downward. It's like that. Fg. And this Fg, if we resolve this force into two components, one will be if this angle is theta, this angle will also be theta. So this force will be Fg cos theta. We are trying to resolve this force into two components. Along the string, Fg cos theta, and perpendicular to that one is perpendicular to the string is Fg sin theta. Now this Fg cos theta will be balanced by the tension. Okay, so T and then Fg cos theta plus Fg cos theta will be 0 because T is in one direction, Fg cos theta is another direction. They are equal and opposite, so resultant will be 0. So only due to the Fg sin theta, it will start to move along that direction. Okay. So the tangential component produces a restoring torque about the pendulum's pivot point because the component always act opposite to the displacement of the bob. So as to bring the bob back towards its central location. That location is called the equilibrium position. That is that location. In that case, theta equal to 0 because the pendulum would be rest there where it is not swing. Okay. So the tau will be minus L, tau equal to R cross F. R is the distance. Nah? So L and the angle between this force and this string L, this angle is 90 degrees. So R cross F means F into this distance L. So this minus sign actually, so tau equal to minus L. L is the distance, the length of the arm of the force, and Fg sin theta is the force. And this minus sign indicate that the torque acts to reduce theta. And L is the moment arm of the force component, and Fg sin theta about the pivot point. So and you also know from the mechanics, tau is equal to I alpha. I is the moment of inertia and alpha is the angular acceleration. So tau equal to I alpha. From there you can derive alpha equal to minus mg L by I into theta. So again the angular acceleration, these are constant for a particular bob, for particular pendulum having mass m and length I. Okay, so it's constant. So alpha is actually proportional to theta. So that means this is the characteristics of simple harmonic motion. So it tells us that the angular acceleration of the pendulum is proportional to the angular displacement, but opposite in sign. So that's the characteristics of simple harmonic motion. So from here, so this is actually alpha equal to some constant of theta. So this is actually omega square. Previously we have seen that A is equal to acceleration A equal to minus omega square x. So if you compare this equation with that one, so omega square will be mgl by I. So omega will be mgl square root of mgl by I. So if you know omega, from there you can calculate t equal to twice pi by omega, twice pi divided by omega. So After simplifying, it T will be twice by root over I by mgl. And for this pendulum, I equal to, it will be, mass is m and distance is l. So it will be ml square. Okay. So if I equal to ml square, substitute the value of ml square, cancelled out, l cancelled out, so it will be T equal to twice by root over L by G. This is the laws of the, you have studied the laws of simple harmonic motion in your college level physics. Now we derive this formula. So from there you can decide that time period is proportional to the root over L and time period is proportional to 1 by root over G. So if you combine these two formula, it becomes equal to twice by root over L by G. So in physics labs, you perform some experiment and determine the experiment on simple harmonic motion, and you determine the time period of the simple harmonic oscillation. Now, simple harmonic motion, simple pendulum is a simple pendulum because there is a mass m and well-defined length L. Okay, so how about you see the everything? We give an example that tree is oscillating. Sometimes building also oscillates. Okay, so that's the real pendulum, or something vibrating or oscillating. That's the real pendulum. So we call it physical pendulum. So physical pendulum, a real pendulum, you usually call the physical pendulum, real pendulum. Like the building that we are sitting here, if it is a high-rise building, so that also getting simple harmonic motion. So and the pivot point of this building is we civil engineer, they do some piling and all those things. The building is pivoted at the ground through this piling and bases and so on. So and the building is, if it is a very tall building, the building started to oscillate. Okay, so in that case, the motion can be complicated because of the distribution of the mass. Okay, like. So we consider this sort of mass. Okay, so in that case, distribution of the mass is not same. So its center of mass is at C here. Okay, so consider an arbitrary physical pendulum displaced at one side by an angle displaced by an angle theta. The gravitational force Fg acts downwards. Fg acts at its center of mass at C here, at a distance h, from the pivot point. This is the pivot point, at a distance h from the pivot point. For a physical pendulum, the restoring again, so Fg cos theta will be balanced by the tension. So due to Fg sin theta, it will start to move. Okay, so the Fg sin theta is the restoring force. It will try to come back its resting point or equilibrium position. So the Fg sin theta of the gravitational force has a moment arm of distance. Moment arm is distance h. Like in case of simple pendulum, this distance was L. Okay. So we can write that time period T is twice by root over. Previously it was I by mgl. Now it will be T equal to twice by root over I by mgh. It's time period. Now previously, in case of simple pendulum, I is just mass multiplied by L square. Now for physical pendulum, so I is called the rotational inertia of the pendulum about the pivot point O. However, now I is not simply mh square. It depends on the shape of the physical pendulum as well. But it is still proportional to m. So a physical pendulum will not swing if it pivots at its center of mass. So if you rotate it, if you hang it over there, so it will not move. We can use a physical pendulum to measure the free fall acceleration at acceleration g, free fall acceleration g at particular location on the Earth's surface. Okay, so now the relationship between simple harmonic motion and uniform circular motion. So in this figure, suppose figure shows a reference particle P prime. This reference particle P prime is moving in an uniform circle. So P prime particle is moving over here with an angular speed omega. The radius, this radius xm of the circle is the magnitude of the particle's position vector. At any time t, the angular position of the particle is at any time, so is angular speed omega. So at t equal to 0, it was here. When it is at time t, and when it is at 0, suppose its phase is phi. So at time t, it moves omega t. So the total displacement will be omega t plus phi. So phi is the angular phase, or phi is the angular position at t equal to 0. Now projection of this p prime, projection of p prime on x-axis will be xm cos of omega t plus phi. On y-axis, it will be xm sine of omega t plus phi. Okay. The projection particle p prime on the axis at a point p, which take to be a second particle. Second particle is here, this one. So it will be xm cos of omega t. Xt will be xm cos of omega t plus phi. And you know that xm cos of omega t plus phi is also the displacement of the simple harmonic motion that we have studied earlier. That means when the particle moves in a circular path over here, then the second particle, like when the particle is here, so its projection on x-axis is there. When the particle moves there, its projection will be here. When the particle moves here, its projection will be here. When the particle is there, its projection is there. When the particle moves here, projection is there. When it is there, it moves here, and so on. So that means this particle moves in a circular path. So, and then that particle will perform a simple harmonic motion along its diameter. So if the reference particle P prime moves in a uniform circular motion, its projection particle P moves in a simple harmonic motion along the diameter of the circle. So in the previous slide, I showed the displacement of the particle, angular displacement of the particle moving in a circular path, which can be explained, which follows the actually simple harmonic motion. Now the velocity, if you differentiate the previous expression, this one xt, if you differentiate with respect to time, dx dt, that will give you the velocity, and it will be this one. Okay, so velocity will be along the tangential part of that one, and then if you differentiate this expression, you will get the expression for the acceleration. Okay, now thus whether, so again the acceleration is proportional to the, you can see that acceleration is proportional to the displacement x. This is x, so a is proportional to x, and it is connected by omega square. So thus whether we look at the displacement or velocity or the acceleration, the projection of the uniform circular motion is indeed simple harmonic. It is indeed simple harmonic motion. So whether you look at position, that means displacement, velocity or acceleration, it actually follow the uniform. So uniform circular motion is indeed a simple harmonic motion. Okay, so now please solve this problem. A block. So there is a small particle having mass m. M is given. Please solve this problem. M is given 600. M equal to 680 gram. So you can convert it into kg. It will be 0.68 kg, and it is fastened, that is tied to a spring whose spring constant is K, and K is given 65 Newton per meter. And the block is, so it's a linear oscillator, and the block is full. So the situation is like that. So that's the base, and you have a spring. And particle of mass m is there. Okay, so its mass is given, spring constant is given. So your task is to and you pulled it 11 centimeter maximum distance, 11 centimeter from its equilibrium position at a frictionless surface, and release it from the rest. So if you stretch it 11 centimeter, so maximum amplitude of the simple harmonic motion will also be 11 centimeter. Now your task is to calculate what are the angular frequency, omega. And previously we have seen that omega is equal to root over k by m. So you know k, you know m, then you can calculate. So it's converted to kg. So that is at this radian per second. Once you know omega, then you can calculate f, frequency of the oscillation. So first part is done. What is the amplitude of the oscillation? I already said amplitude of the oscillation will be amplitude is called the maximum displacement. So maximum displacement will be 11 centimeter. If it is frictionless, then still it will go in this side, it will go to 11 centimeter. So maximum amplitude is 11 centimeter. And then your task is to calculate the speed of the oscillating block. And we have derived a maximum speed. So maximum speed is like our maximum speed is actually, it will be omega into xm. So you know the value of omega, and also you know the value of xm. So bm will be omega xm. So this is omega, and xm is 11 centimeter, means 0.11 meter. So we have 1.1 meters. So maximum speed occurs when the oscillating block is rushing through the origin. We have seen it earlier, because at the extreme point it will have potential energy. So when it moves to the equilibrium position, so its kinetic energy maximum. So kinetic maximum means maximum speed occurs at the equilibrium position. That means at x equal to 0. And then your task is to calculate, what is the next part? What is the magnitude m of the maximum acceleration of the block? And what is the phase constant phi for the motion? Okay, so to find out the maximum acceleration, we know that at t equal to 0, the block is located, at t equal to 0, the block is located at x equal to xm. Substituting the initial condition in the displacement expression and cancelling xm gives us 1 equal to, because you know the x equal to xm cos of omega t plus phi. From there you can calculate phi equal to 0. And then xt is xm cos of omega t plus phi, xm is this, cos omega is this, and phi equal to 0. So that's the expression. Okay. And the next problem is finding a simple harmonic motion phase constant from the displacement and velocity. So at t equal to 0, the displacement x equal to 0 of the block in a linear oscillator is minus 8.50 centimeter. That means you compress the spring now. You compress the spring. So its displacement is minus 8.50. You just compress the spring of length 8.50 centimeter. The block velocity v0, then v is given there, and its acceleration is given here. Now, what is the angular frequency omega of the system? So from the previously we have seen that we can calculate omega is actually a by square root of a by x0. because A is actually omega square x. We know acceleration is minus omega square x. From there, we can calculate the value of omega. So value of omega will be this one. That's the one, omega square xm. So when this 0, A is this one. Okay, now what are the phase constant phi of the amplitude at xm? So to find out the phase constants, so the problem is already solved here. Okay, I hope you will be able to catch it up. Or from here, xm equal to x0 divided by from this expression, x0 divided by cos phi. So x0 is given minus 8.5 centimeter. Cos phi, you calculate phi from these expressions, d0 by x0, 10 pi. Okay, and when you solve this equation, phi will be either minus 25 degree or on 155 degree. So if you choose phi as 25 degree, xm will be this one. If you choose phi as this, acceleration will be positive one. So one is in the extreme right, xm, maximum amplitude in the right position, and maximum amplitude in the, and this is the maximum amplitude in the left position. So this is exactly the same. Okay. So in the exam, we might set similar sort of problem. Okay. Now, so far we have studied the oscillation of a single particle. Okay. However, sometimes the oscillations are coupled. Even you see in your first semester, not first semester, even before midterm, we have studied structure of matter. That means every matter actually composed of large number of atoms. And above absolute zero temperature, these atoms are vibrating. So these atoms in a solid state, these atoms, there is an interaction between the atoms, okay, which is called the bond in solid we have studied. So these bonds actually similar to the some scientists explain that when in a solid material, two particles are just like, you can assume that these two particles are attached like a spring. So it will be in 3D in all directions. So in that case, so there will be an oscillation above absolute zero temperature. So that oscillation will not be the oscillation of a single particle. So oscillation of all particles coupled together. Okay. So before studying these complicated oscillations, we are studying two-body oscillations. Suppose one particle having mass m, another particle m1 having particle 1 having mass m1, particle 2 having mass m2 are connected with a spring of spring constant k. Okay, so like in a diatomic molecule, two atoms are bound together with a force, which is called the binding bonds between them. If displaced a small distance from its equilibrium position, molecule will oscillate about the equilibrium position. Let us suppose that the molecule can be represented by, as I said, two particles of masses m1 and m2 connected by a spring of spring constant k. The relative separation. So if this is origin, position of this particle is x2, position of this particle is x1. So relative position will be x1 minus x2, gives the length of the spring at an instant. If the unstretched length of the spring is L, then the change of the length of the spring is x1 minus x2 is the relative distance between them. So and sometimes they'll be compressed and sometimes they will be expanded. Okay, so the length of the spring will be x1 minus x2, and then you have to subtract the original length of the spring, and magnitude of the force that the spring exert on each particle is F equal to kx. That's because the spring constant is k and the stretch portion is x, so force will be F equal to kx. If the spring exert a force minus F on particle 1, then it will exert a plus force over here on M2. So for the first particle, you can write the equation of the simple harmonic motion will be m1 d square x1 dt square equal to minus kx. For the second particle, the equation of the motion is the positive force kx. We have already explained. If the minus force acts on particle 1, then plus force will be particle on 2. Now, if you multiply both sides of this equation by m2 and both sides of this equation by m1, so if you multiply it by m2, this becomes this one. If you multiply this equation by m1, this will be this. Now, if we subtract this from that one, okay, so you'll get this thing. And if you simplify this equation, how to simplify? If you divide both sides by m1, m2. Take m1, m2 common and then divide it by both sides. So m1, m2 will be cancelled over there. Or m1, m2 divided by m1 plus m2 d square, and then x1 minus x2 dt square will be minus kx. Now, if we express this one by a mass m, okay, so actually m1, m2 divided by m1 plus m2 has the dimension of mass, because this will be m1, m2 mass square divided by mass. So it will be the dimension of the mass. And this quantity m1, m2 by m1 plus m2 is called the reduced mass of the system. Okay, and d dt of x1 minus x2 is actually d dt of, from the previous expression, d dt of x1 minus d dt of x plus L. Okay, d dt of x plus L. So L is constant, and derivative of that one will be 0. So it will be just dx dt. So we can rewrite this equation as like m d square x dt square equal to minus kx, or d square x dt square equal to minus k by mx. So which is and another k by m is omega square. Okay, which is precisely the simple harmonic motion. Now in this case, m will be so equation 24 is identical to the differential equation of simple harmonic motion of a single oscillating mass. The frequency of the oscillation is nu equal to frequency of the oscillation nu will be 1 by t. So that will be 1 by twice pi root over k by m. Now in this case, m is connected like 1 by m equal to 1 by m1 plus 1 by m2, because you know that m is m1 m2 divided by m1 plus m2. So here m is the reduced mass of the system. It will be noted that the reduced mass is always less than that of the either mass of the system. If you look at their reduced mass is m1 m2 by m1 plus m2. So it will be always less than m1 or m1 and m2. So that means it behaves like in an electrical circuit when you connect two resistance R1 and R2 parallel. Their equivalent resistance R also follows this formula, 1 by R1 plus 1 by R2. and this R is always less than R1 and R2 in case of parallel circuit. So similar sort of things happens here. When two particles are connected with a spring, okay, so their equivalent mass is always less than that of the either masses of the system. So from this notion, you can calculate the time period, you can calculate the angular frequency, and so on.